Hello there! In this video we will be primarily discussing the concept of a monoid and how it relates to the other algebraic structures we have discussed so far. We will begin by quickly going over what it means for an algebraic structure to be a magma and a semigroup, then we will introduce the concept of an identity element, and then introduce the structure known as a monoid. Throughout the video we will give 3 examples to measure your understanding. Feel free to give your answers in the comment section below. Let's get started. Alright, so let's just quickly go over some of the basics that we discussed so far, in particular the concepts of magmas and semigroups. So let's begin by defining X to be the pair S with some operation star. So star is a binary operation from S cross S into S. So the first structure that we talked about was magmas. So if S is closed under this binary operation star, then we say that X is a magma, and if X is a magma and star is associative on the set S, so X is an associative magma, then we call X a semigroup. So those are the 2 concepts we have so far, magmas and semigroups. So let's define the first basic tool that we're going to be needing for our discussion on monoids. So definition. So let S be a non-empty set, and let E be an element of S. So it's a particular element in this particular set S. So what special characteristics must this E have, and why do we care? So E is called an identity element of S. So notice the word choice that we're using here. We're saying an identity element. We're not calling it the identity element. So we're not going to imply that the identity element is unique in this case. In fact, you can have several identity elements, but we're going to go into that in a deeper discussion in just a moment. So we're not claiming uniqueness quite yet. So E is an identity element of S if the following conditions hold. So if X star E is equal to E star X, and that's going to be equal to X, and this has to be true for every X in this set S. All right, so that's the definition of an identity element. So as usual, let's look at a couple examples to sort of get an idea of what we have going on here. So example 1. So let us define S to be the set containing the values alpha and beta. And let's define the binary operation star in the following way. So let's have alpha beta there. And let's alpha alpha be equal to alpha, alpha beta be equal to beta, beta alpha to be equal to beta, and beta beta to be equal to alpha. So you should be able to verify by now whether this is a magma and a semigroup, but we're not going to get into that quite yet. So our goal is to see if S has an identity element. So does S have an identity element? Okay, so let's just look at a couple things here. Let's first off look at A star, alpha star alpha. So clearly alpha star alpha is equal to alpha, right? So it's possible that alpha is an identity element in this case, right? So alpha star alpha is of course equal to alpha star alpha, which is equal to alpha, right? So I'm sort of focusing on this. Alpha, so is this the identity element? So that's the first question we have. So now we need to look at beta and test that out. So beta star alpha is equal to what? So beta star alpha is equal to beta, and alpha star beta is equal to beta as well, right? So that is both true. So therefore, And notice that we've covered all of the values in S. So we've covered alpha and we've covered beta. So therefore, alpha is the identity element of S. Right? So that would be how you can algebraically determine whether a particular element in the set is indeed a identity element. You can also sort of look at the table that we have selected here, and you should see some symmetry going on here as well. So if you look at here, if we do, for example, beta star alpha, right? So that's that beta value there. And if we do alpha star beta, then we have b's there. So they should be symmetric values there, and we also see some symmetry on the diagonal as well. Alpha star alpha and alpha star alpha is equal to there. So you should be able to sometimes see if there is or is not an identity element if there is some symmetry, but don't always jump to that conclusion because sometimes it might not totally be symmetric, but there is some identity elements present in that particular. Let T be the set containing the letters gamma and delta, and let capital Delta be defined on T via this following table. Does T have an identity element under delta? Explain. All right, so let's jump back into this particular example of this particular set S that we've defined via this table. So we've already figured out that this set does have an identity element, and that is precisely the element alpha. So let us actually go through the process of seeing whether this is a magma and moreover a semigroup, and then we're going to introduce what it means to be a monoid. Okay? All right, so question. Is S closed under the binary operation star? So we should be able to see this clearly from the table. So all the elements in the outputs of this function are elements of the set S, right? So all these values here are elements of S, so that means S is closed under star. So that means X is equal to S star is a magma, right? So now let us see if it is associative, right? So how would you test that? Okay, so associative, so is star associative on this particular set S, right? So we need to show a bunch of things, right? So we need to show that alpha star beta star alpha is equal to something, in particular alpha star beta star alpha. Right, so that's going to be equal to beta star alpha, which is going to be equal to beta, and this is going to be alpha star beta, which is going to be equal to beta. So this checks out. And there are several other things that we need to show here, right? So we actually went through this example before. Remember, since S has two elements, we have 2 times 2 times 2, which is equal to 2 cubed, which is equal to 8. Different pairs to check here. And you can actually show that all of them actually do satisfy, right? After that long, tedious process. So therefore, we should be able to see that this set is associative under star. And furthermore, that means X is equal to S star is a semigroup. And why is it a semigroup? Well, first off, it is a magma, and it's an associative magma. Therefore, this structure, S star, is a semigroup. And in addition, we have that this semigroup has an identity element. So do you want to take a guess at what a monoid is going to be defined to be? So you can give a guess. So definition, let X be equal to S star be a semigroup. If S has an identity element under this binary operation star, then X is called a monoid. So a monoid is a semigroup that contains an identity element. Okay, so let's look at a particular example, and this example is actually quite important. So let's consider the set S to be equal to the elements -1, 1, I, and minus I, where I is the square root of -1. And let's define star to be equal to ordinary multiplication. So ordinary multiplication in the set of complex numbers. Okay. So at a previous exercise, you were asked to show that X, which is equal to S star, is a semigroup, right? Because when you multiply all of these elements together, that clearly is an element of S. Associativity for S is inherited from the associativity of the set of complex numbers, right? So what is the identity element of this particular set S? And you might be able to guess, well, we're under standard multiplication, so 1, which is the multiplicative identity for C, should be the multiplicative identity for this particular set S. And you should be able to verify that 1 star X is actually equal to X star 1 is equal to X, and this is going to be true for all X in S, right? So you should be able to verify that that is the case for all 4 values in this particular set. So if that is the case, that means 1 is the identity element of S under star. So since we have an identity element for this particular set S, and X is a semigroup, therefore X is a monoid. Let X be S star, and let S contain alpha, beta, gamma, and define star on S by the following table. Is X a monoid? Justify why or why not. So let us experiment with the idea of possibly having more than one identity element in that particular set. So let's look at just a couple examples, and we're going to increase the number of elements in the set to 3 instead of 2, because 2 usually is a bit trivial. So let's look at a particular example. Let's look at the set S containing the values A, B, and C. Let's define a new element operation delta via the following table. So let's do A, B, and C, A, B, and C. Okay. So let's see if we can try and complete this table and sort of build a definition for the operation delta such that it does have an identity element. So if we do A, B, and C across the first row, what are we sort of allowing here? So we're allowing A star A to be A star B to be A, and A star B to be B, sorry, and A star C to be equal to C. So notice what we're doing here is we're sort of building an identity element on the left-hand side. So this is what some people usually refer to as a left identity element. Similarly, if we go down the column, and we look down that way, so if we do, for example, A, B, and C here, so what we're doing A star A to be equal to A, B star A to be equal to B, and C star A to be equal to C. And if you sort of look at here, what we're doing, so we're getting the same exact element back again, so this is what we usually refer to as a right identity element, right? So in this particular state, so this forces both of these. So this forces x star e to be equal to e star x to be equal to x, where the identity element e is equal to a in both of these cases, right? So that's not really very special because, we're choosing the same exact a in both of these to be equal to the left and right identity. And usually when we have both left and right identity, usually we combine them and we call it an identity element, right, together. So if it's a left identity and a right identity, both of them, then we call it a identity element. And you can probably try to explore how you can fill in this table. So one way you could do this is we could put C down the diagonal. You could put A there, you could put A there, and you could put B there, right? And you should be able to see that this group is sort of similar to the group Z modulo 3 under modulo 3 addition. And you should be able to see that they have sort of the same exact structure, and we're going to talk about similar algebraic structures a little bit later. But that pretty much creates a table that has a unique identity element. So let's try and build a set that actually might have two different identity elements. All right. So let's consider another element. Let's call it star. I like star. So let's do A, B, and C. A, B, and C. So it's the same exact elements, just a different operation. So let's put an A there, and let's actually put a C there, right? And let's actually put a C here, a B here, a C here, and a C here. And let's leave the other values blank, right? So I'm not going to put an element there, an element there, an element there. So before I actually start talking about the possibility that this has more than one identity element, or at least a different left and a different right identity, I just want to sort of talk about what type of operation we have going on here. So if we have blanks in this operation table, for example, B star A and C star C, and somebody asks you, well, what is B star A equal to? What is C star C equal to? And what is A star B equal to? So the answer to all of these is undefined, right? So this is sort of like the 1 divided by 0 thing. So there's no number in this particular set S that is defined as the output of these two input values. Some people will also say that star is not everywhere defined on this particular set S. But it's extremely important that you know the difference, that this is not equivalent to saying that this is not well defined. So when someone says that something is not well defined, that usually implies that there is some ambiguity or some unclearness as to what the value might be equal to, right? For example, if you have one happy person plus one happy animal, when you add those two together, do you get happy animal and a person, or do you get like a couple, or do you get like a family, like a pet or something like that? Like the addition in that particular stage is not really clear, or possibly they make clear to different people, right? Different perspectives might have that same exact meaning, right? So let's go back to this discussion of possibly having two different types of identities here. Okay, so let's look at this particular table. So let's look at A star A. So we clearly see that that's equal to A. A star C is equal to C, and C star A is equal to C. Right? So A star A is equal to A, and A star C and C star A is equal to C. So these two operations will imply that an identity element E is equal to A, right? At least a first identity element. Now, if we look at the other operations, for example, B star B, B star C, and C star B, so B star B is equal to B star C is equal to C, and C star B is equal to C. So if we look at here, so we have B star B, B star C, and C star B. So these operations will imply that another possible identity element is equal to B. More in particular, what we have going on here, they pretty much act as left and right identities, right? So this is a left identity for B, this is a right identity for B, this is a left and this is a right identity. So it's possible that they're moreover not just left and right identities, but they could just be identities for this whole entire set. But so far for this particular operation, it's not everywhere defined. So one of my last questions that I'm going to leave you with is it possible that you can fill in these three blanks with either A, B, or C, not more than one, else you have some well-defined type of issues, such that this particular set, I'll call it, say, omega is equal to S star. Is it possible to fill in those blanks, those three blanks, such that omega is a monoid? Let omega be S star, and let S contain ABC, and to find star partially on S to be this following table. Is it possible to complete the table for star in order to make omega a monoid? Justify your answer. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.